Reusable rocket landing legs are lightweight, aerodynamic support structures that deploy just seconds before touchdown. They cushion the rocket's impact during vertical landing and keep the massive booster stable on solid ground or drone ships. They are imperative for rockets as they keep the rocket safe and avoid destruction. In today's video, we will be exploring the parts of a reusable rocket leg, the deployment mechanism, the future of reusability, and examples of reusable rocket legs. Reusable rocket legs have three parts: the strut, the footpad, and the deployment or locking mechanism. The main strut is the structural framework that absorbs the immense kinetic energy of landing. It is made up of three parts: the primary strut, the auxiliary or stabilizer strut, and the dampers. The primary strut is the main vertical or ankle support connected to the rocket's body. The auxiliary or stabilizer struts are support rods, often forming a frame shape with the main leg, that provide lateral stability or prevent the leg from buckling under horizontal forces. Dampers are integrated hydraulic, pneumatic, or crushable systems like aluminum honeycomb that compress to dissipate impact force and absorb the shock of touchdown. The footpad is the flat, circular base at the bottom of the landing leg that makes contact with the earth. It has two parts: pivot joints and wear pads or skids. The pivot joints connect the footpad to the struts, allowing it to swivel or adjust to the uneven terrain on the landing pad or drone ship. Wear pads or skids are durable surfaces on the bottom that can withstand friction and heat of lateral sliding during touchdown. The deployment and locking system is the hardware responsible for releasing, extending, and locking the legs into place. It has four parts: the launch, lock, and release mechanism, pushers, telescopic extenders, and the locking mechanism. The LLRMs are latches that secure the leg tight against the rocket's body during ascent and atmospheric re-entry. Pushers are pneumatic actuators or spring-loaded triggers at the top of the rocket leg that forcefully push the rocket leg out to initiate deployment. Gravity and airflow then assist in fully extending the legs. Telescopic cylinders are nested cylinders, or cylinders that slide inside another cylinder that extend the leg downward to its maximum length. Finally, the locking mechanism has heavy-duty locking pins or springs that engage the moment the leg is fully extended, locking it rigidly so it cannot collapse backward or rebound upon impact. Reusable rocket legs are stowed flat against the rocket during ascent to reduce aerodynamic drag. In summary, during the final descent, the rocket uses rapid pneumatic or gravity-assisted mechanisms to release, flip out, extend, and lock into place for a safe vertical touchdown. We will be exploring the different phases now. A boost back burn reverses a rocket booster's direction to send it back towards the landing sites, while an entry burn acts like a set of brakes to slow the rocket down as it enters the thicker part of the Earth's atmosphere, preventing it from overheating. During the rocket's boost back and entry burns, the legs remain secure by upper mechanical latches and hold-down devices. When the rocket is seconds before touchdown and the speed drops to a hover, flight computers signal the release of these locks. Small pneumatic pushers, often powered by high-pressure gas such as helium, provide an initial instantaneous thrust to push the rocket legs slightly outward, not completely out, and overcome static friction, the force required a rocket to move. Once the locks are released and the legs are pushed outwards, the system largely relies on gravity. No heavy hydraulic systems are required to extend the legs. The natural weight of the legs, combined with aerodynamic forces and the vehicle's downward atmospheric acceleration, causes them to swing open rapidly and smoothly. Telescopic extenders are collapsible engine nozzles attached to the bottom of the engine in order to create thrust and use fuel efficiently. As the leg swings outward from the vehicle body, built-in deployment arms and telescopic extenders unfold the structures into a wide, stable stance. forming an A-frame structure. Once the legs reach their fully extended position, heavy-duty mechanical locks snap into place. This rigid locking is critical as it prevents the legs from collapsing under intense vibration and impact forces of landing. At the exact moment of touchdown, the shock absorbers, often using crushable structures like aluminum honeycomb, compress to dissipate the tremendous kinetic energy of the rocket, preventing it from tipping over or experiencing structural failure. After this happens, you can safely announce that the Eagle has landed. The future of reusability is shifting from traditional deployable landing legs to towering launch tower catches, enabling rapid turnaround times and cost reductions. While partial reuse remains the standard, the industry is racing towards fully reusable two-stage to-orbit vehicles. To increase payload capacities and decrease weight, massive vehicles have ditched traditional landing legs. Instead, the booster is caught mid-air by mechanical arms on launch towers, streamlining immediate refurbishment and stacking, which essentially means restoring the rocket to be used immediately. For vehicles still utilizing landing legs, leg mechanisms are evolving to be lighter, more durable, and capable of automated self-leveling to handle diverse, uneven terrain on off-world or downrange landing pads. Off-world landing pads are built on extraterrestrial surfaces like the Moon or Mars, while downrange landing pads are landing pads located far away from the launch site on Earth. The next frontier is achieving fully reusable second stages. Companies such as Stoke Space are working on atmospheric entry shielding and mechanical recovery systems to reuse upper stages, further driving down the cost of access to orbit. Immensely strong and lightweight, modern rocket landing legs have revolutionized spaceflight. These remarkable landing systems feature several cutting-edge designs and engineering breakthroughs. The Falcon 9 uses 4 deployable carbon fiber and aluminum honeycomb landing legs. They are stowed tightly against the rocket's body during ascent to reduce aerodynamic drag, and they are deployed using high-pressure helium or nitrogen just seconds before touchdown. The legs feature a crush core design, absorbing the massive kinetic energy by permanently deforming during impact. Because the Moon lacks launch towers or flat concrete pads, the lunar variant of the Starship requires highly specialized landing legs. Standing 50 meters tall and carrying heavy scientific payload, the vehicle has a very high center of gravity. To prevent it from toppling over on the uneven lunar surface, these massive legs spread across an incredibly wide footprint. They are built from reinforced stainless steel to withstand extreme thermal shock. Blue Origin's heavy-lift New Glenn rocket utilizes a different design for its reusable first stage. It features robust landing gear that must handle the dynamic forces of landing on a moving ocean platform. To ensure the heavy booster does not tip or slide on an oscillating ocean vessel, the legs are built to retract quickly to ensure they can be moved from the platform and onto land. Callisto, cooperative action leading to launcher innovative stage test operations, that's a mouthful, is an experimental reusable rocket being developed by several international space agencies. Its landing mechanism is impressive due to its retractable telescopic primary strut and pneumatic folding mechanism. Designed specifically for its autonomous pinpoint landings, the legs must maintain ground clearance and limit load transfers to the vehicle structure during touchdown. To save significant weight and maximize payload capacity, SpaceX opted to remove landing legs entirely from their super heavy booster. Instead, they rely on Mechazilla, a massive launch and catch tower equipped with mechanical arms that catch the descending booster in mid-air. And yes, the name was inspired by the monster Mechagodzilla from the Godzilla franchise. While not a physical leg on the rocket, this innovative catch system represents a massive evolution in landing architecture. Thank you for watching this video on reusable rocket legs for space exploration. Next video, we'll be exploring how rocket engines steer using the gimballing system. Don't forget to like, subscribe, and hit the notification bell to never miss a video. Bye!